In this video, we're going to discuss the generation of surface waves in the ocean. So to generate a wave, you need three components. You need something that disturbs the surface of the medium. So in our case, the medium is the surface of the ocean, so the water surface. Then you need a restoring force, something that tries to flatten out that medium. So in our case, that would be a force that returns the water surface to flat, as if there wasn't a wave there. And finally, you need the restoring force to be strong enough that it overshoots the reference level and then causes an oscillation, so the surface comes back up and goes back down, etc. So in the ocean, there are a number of possible ways of disturbing the ocean to initiate a wave. The most common is wind, which we will talk about shortly, but other things like raindrops, pebbles, landslides, underwater volcanoes, underwater earthquakes, which cause tsunamis or potentially cause tsunamis. And then this is a video shot from a research vessel in Antarctica. You can see the ice shelf carving away, so essentially a landslide but of ice and ice fall. And then that displaces the water surface and creates a wave, as you can see coming towards the vessel now. So as I said, the restoring force tries to flatten out or return the system to its initial state. This is a classic example of a weight hanging from a spring. So here I've drawn it in its initial equilibrium position where the tension in the spring is exactly balancing the mass of the weight. So if we were to pull the weight down and extend the spring, then it's going to want to spring back up. It's going to overshoot and then go up and down. So it goes up, so the mass is too heavy for the spring, so it falls back down, overshoots. And in this case, there's no friction in the system, so this will just keep going and going. But in reality, friction will damp out the motion and it will eventually stop. So there are different types of waves in the ocean. So this table lists a number of them. So the first column is the wave type, or the name of the wave. Then the disturbing force, then the restoring force, and then in the last column are some typical wavelengths. So that's the distance between consecutive crests. So the smallest waves in the ocean are capillary waves. So they have wavelengths of less than 2 centimeters or less than 3/4 of an inch. And it's surface tension that is the restoring force. You're probably familiar with surface tension from seeing photos of insects walking on water, so they are using the surface tension of the water to hold themselves up. Capillary waves are generally generated via wind. The most common waves in the ocean are wind waves, so they're obviously generated by the wind. They're now long enough that gravity is the primary restoring force. The next waves here are the seiche. So these are oscillating motions in an enclosed basin. Primarily, this is seen in harbors and lakes. The fourth line of this table is about tsunamis. So they're generally created by earthquakes, undersea earthquakes. They have gravity as their restoring force, and they have wavelengths of a couple hundred kilometers. And the last line on this table is tides, which we will talk about in a separate section. They are forced by the gravitational forces in the Earth-Moon system and the Earth-Sun system. Gravity is their restoring force. So if we look at the information in a slightly different form, on the horizontal axis here, we have the period of the wave, so 100th of a second, 1 second, 10 seconds. So this is the time between consecutive crests. Under here, we have that same information, but in frequency. So a 1 second period wave corresponds to a 1 hertz frequency. A wave with a period of 1/10 of a second corresponds to a 10 hertz frequency. The orange curve here shows the amount of energy in a frequency or period band. So the largest amount of energy here is at the sort of within the 1 to 10 second periods. And this is the primary period of wind waves. And we have some energy in the capillary waves, some in the seiches, Tsunamis are a very episodic thing, but there's definitely energy in there. And then up here we have the tides. The process by which wind waves are formed in the ocean is we start off with a flat surface, and then the wind blows over that. So just the friction of the wind on the surface will start to essentially crinkle up the surface, so we form capillary waves that way. Once a wave is formed, a capillary wave is formed, now we have a structure that the wind is pushing against. So if the wind's coming left to right in this image, is now pushing against an upward face on this side, so we have increased pressure going on this side, and then the wind comes up and over, and it actually creates an area of low pressure on the downward side. So both of those, the positive pressure and the negative pressure, work to grow the wave. And as the wave grows, the amount of this pressure difference increases. The extent and magnitude of wind-driven waves depends on three things: the wind strength, the wind duration, so the amount of time the wind blew, and then the fetch. So this is the uninterrupted area over which the wind blows. So in terms of a passing storm, the wind duration is only the amount of time that the wind is blowing on a particular part of the ocean, a particular section of the ocean, rather than the duration of the storm. It's this fetch that explains why you sort of get a younger, choppier sea in a Kona wind on the south shore of Oahu than you do under trade wind conditions. So under a trade wind, the wind is coming over the island, so it hasn't actually blown over too much of the water when it gets to the south shore. Whereas a Kona wind is not interrupted by the island before it gets to the south shore, so you have a much larger fetch. So the duration and wind strength can act over a much larger area and generate the wind waves. Wind blowing over a part of the ocean will build up larger and larger waves, well, at least up to a point. So this sort of chaotic combination of waves that you can see in this photo is known as a sea. Recapping all of that, we have on the left-hand side, the wind blowing over the surface, the friction crinkling up the surface, giving us the capillary waves. Then that wind is now blowing on a wave, so we get the pressure differential across the wave that builds the wave up. It's gone from being surface tension dominated for the restoring force to gravity dominated. As the waves keep growing, at some point the height to width ratio will get greater than 1:7. So the wavelength is less than 7 times the height. If we had a wave with a wavelength of 7 meters, then a 1 meter wave height would give you the 7:1 ratio. So once it exceeds that 7:1 ratio, it starts to break. And so you get these white caps on the top of it, which I'm sure you've all seen looking out over the South Shore or any part of the ocean on a windy day. You get the white caps forming out there. And that's this breaking of steep waves to get what's known as a fully developed sea. So this is sort of this messy combination, but with the maximum size waves theoretically possible. You need the wind to blow over the same part of the ocean, so over a given fetch, for about 3 days. Just another view of it, we have the wind coming across our fetch, and so you get all this choppy stuff, then you get a fully developed sea, and then once it gets out of the influence of the wind, then it starts to propagate away as an unforced wave and will eventually turn into the cleaner swell waves that people like to see at the beach. As you can see in the photo, a fully developed sea contains a range of wave heights in it. So the way that people classify the wave height is with the concept of a significant wave height. So this is where you take the waves during half an hour or some defined period, and then you take the largest 1/3 of those waves that you measured, and then you take the average of that largest 1/3, and that gives you the significant wave height. Turns out this significant wave height measurement is pretty close to what most people will say if they're on a boat and asked to say how big the waves are. In this figure here, we have significant wave height measured by satellite. The bright colors are bigger waves. The purple colors are small waves. The top panel is during Northern Hemisphere winter, and the bottom panel is during Northern Hemisphere summer. As you can see, during the winter, we have strong waves coming out of the North Pacific and North Atlantic. So these are the storm belts. So large waves generated under the storms around the Gulf of Alaska and North Atlantic. In the Northern Hemisphere summer, there's a lot less storms in the Northern Hemisphere, so the waves heights decrease there, but there's a lot more wind and storms in the Southern Hemisphere, particularly around the Southern Ocean, where you can get large winds blowing over a very long fetch because the Southern Ocean isn't broken up by any land or continents. So this is a figure from a wave buoy in the Southern Ocean, south of New Zealand. A wave buoy is a float that contains accelerometers. So as the wave moves it up and down, you get acceleration, and from that you can get the displacement or the height of the wave. And a number of wave buoys allow you to also get the direction of the waves that are coming past. So if we concentrate on the two blue shaded areas here, we have at this point the peak of the wave. So a particular wave went past the wave buoy that had a height of 23.8 meters, about the size of a 7-story building. And then the significant wave height, so the average over the largest 1/3 over a period of, I think in this case, half an hour, was 14.9 meters. Depending on the size of the fetch, the strength of the wind, the duration of the wind forcing, you get different theoretical maximums for the waves that can be generated. So in this table, we have wind over a particular fetch, the size of that fetch, the duration of the wind forcing, and then the characteristics of the waves generated. So wave height, wavelength, wave period. And you can see that in the Southern Ocean, on the bottom line there, you can get very strong winds over a very long stretch for a very long time, and you can get waves of 14, 15 meters, significant wave height.